Okay, so we're going to do a little demonstration here of the effect of inductance. And we've built a little circuit based on two MOSFETs. So the signal comes into the first MOSFET and then gets amplified and then is driven into the second MOSFET. Now we have to be aware that there are little capacitors that are intrinsic to the gates of the MOSFET. This is the gate source capacitance. Here we have the output, and we're going to study how the output looks relative to the input for different kinds of connections between them. So here's the first connection right here. It's this little gray wire. It's a little hard to see, so we'll zoom in. So that gray wire connects the drain of the first MOSFET to the gate of the second MOSFET. So the second type of connection we're going to study is this yellow wire, and with this little switch we can replace the gray connection with this yellow, and it's exactly the same. The only difference is you can see it's longer. Then the final one we're going to study is this inductor. So this is a long coil of wire that we just made by hand, and we actually have here a little iron piece that we can stick into the inductor to change the magnetic field and the magnetization inside that inductor. So now let's see what those three different types of interconnects do to the output. Alright, so here on the top in yellow we have the input signal that's going into the gate of the first MOSFET. On the bottom we have the output. So this has been through the inverter chain, the two inverters. And you can see that it's a pretty good square wave, but there is a little bit of oscillation that you can see on some of these traces. And we're going to try to understand what the origin of that oscillation is. This is, by the way, with the gray wire connected. So we're going to show you now what it looks like with that loopy yellow wire that I showed you, the second wire connected. We'll connect it in, and you can see that now there's a lot more oscillation visible. Let's switch it back out, switch it back in. Yeah, so this has increased the amount of oscillation during the transition. Now let's add even more wire. So we're going to go to the black solenoid that we wound. And you can see not only is there a ton of oscillation here, but the oscillation is so big that the second MOSFET is actually not even turning on in some of these situations. It's actually staying off. And so you're getting these big spikes. So now we're going to try it. We're going to try to insert a little piece of magnetic material into the solenoid to see what the magnetization effect is on the circuit. And you can see a major effect here. So what we're doing is we're changing the inductance of that solenoid by changing the magnetization of the core. And as we do that, it shifts back and forth, the oscillation shifts back and forth, and the amplitude becomes larger and smaller, and so we end up with more or less a switching effect. So you can see from this that the amount of inductance in the MOSFET is important. Yeah, so what we saw here was that with the short gray wire there was very little oscillation. With this yellow wire there was more oscillation. And when we took this big solenoid we actually saw a lot of oscillation. And the way we interpret this is that this wire here is actually not a perfect wire. It actually has some intrinsic inductance with it, even when it's not wound in a tight loop. And that inductance interacts with this capacitor to give us this oscillation effect.
In this circuit here, there's three elements that are contributing. The two that are creating the oscillatory behavior are this capacitor and the inductance, the parasitic inductance of this wire. And so basically the circuit that is oscillating starts up here, goes through the power supply, then comes down through the ground, through the inductor and back. And that's the RLC circuit that results in this oscillatory behavior that we're seeing.